Hopefully not. Okay.
Well, let's continue with this morning's session. Our next speaker is Strominger from Harvard University, and who will be telling us about chiral gravity in 3 dimensions.
Okay, thank you very much, and thank you to the organizing committee for the invitation to speak. I'm going to talk today about some recent work, a series of papers over the last 6 months or something, with some students at Harvard, Dionysius Aninos, Tom Hartman, Wei Li, Miga Padi, and Wei Song. So far, string theory is the only known consistent quantum theory of gravity which is complex enough to contain black holes. And there are many aspects of quantum gravity that we'd like to study, and we've done so successfully over the years in string theory. But it would be really nice if we had some simpler examples. And for example, in 2 or 3 dimensions, that would give us some insights into the basic mechanism for reconciling quantum mechanics and gravity without having infinitely many new states. Now, it could be, of course, that you just absolutely need infinitely many new states, and that's the reason that we haven't really come to a good understanding of quantum gravity in 2 or 3 dimensions. However, that's not clear, and people have been studying quantum gravity in 2 or 3 dimensions for 30 years now, and oddly, we still don't really know if there is a fully consistent theory which is complex enough to contain black holes. Of course, one can always write down a trivial theory with no dynamics in it, so that's why I'm qualifying it like that. So in this talk, I'm going to explore a new possibility for a theory of gravity called chiral gravity in 3 dimensions. Now, in 3 dimensions, if you take pure Einstein gravity, at first sight, so I've also with a cosmological constant here, at first sight it looks completely trivial because there's a simple formula that relates the Riemann tensor to the Ricci tensor. So if you fix the Ricci tensor to be a constant, you fix the Riemann tensor to be a constant. In 3 dimensions, the Riemann tensor and the Ricci tensor have the same number of independent components after you take into account the symmetries. So Einstein equation completely fixes the curvature, which means that all solutions are locally constant curvature, and there's no room for any non-trivial dynamics. So at first it looks too trivial, but then in the early 80s, BTZ found that it actually, surprisingly, it contains black holes, and any theory which contains black holes can't be trivial, or it can't be both trivial and consistent because black holes have many, many degrees of freedom. So then in the late 80s, Wittens proposed an exact solution by mapping it to a Chern-Simon gauge theory, but this proposal didn't have many states in it. It didn't explain the black hole entropy. Ultimately, the partition function was not modular invariant, and I think it looks like this is not really the right way to think about quantum gravity and Einstein gravity in 3 dimensions, as Wittens himself said in a recent paper about a year ago. So there's an open question, which I'm not going to address today, which is really an outstanding open question, which is there a consistent quantization of Einstein gravity with, well, for black holes you need the negative cosmological constant. Is there a consistent quantum theory of pure 3D Einstein gravity? And I think it's, maybe I'm wrong, but I don't even really think there's a proposal on the table now for how you would do that. Now, I'm not going to talk about the pure theory. I'm going to talk about a very interesting and I think much overlooked modification, very natural, mathematically natural modification of Einstein gravity that was proposed in the also in the early 80s by Desser-Jakiv and Templeton. And one takes the pure Einstein theory and adds to it the Chern-Simon term. And this is the thing that, were you in 4 dimensions, this is a 3 form, and were you in 4 dimensions, which we're not, we're in 3, but were you in 4 dimensions, if you took its curl, you would get R wedge R. Now, even though the Chern-Simon term itself is not gauge invariant, if you vary it, it is gauge invariant up to a total derivative, and if you vary it, you get a gauge invariant equation of motion, which I've written here, and you get something on the right-hand side which is parity odd, and it's known as the Contin tensor. Now, it's easy to see from this equation of motion that every solution of the Einstein equation, in other words, every constant curvature metric, is also a solution of topologically massive gravity, which I'll call TMG, because here you have derivatives of the curvature, and those will all vanish, so both sides of this equation will vanish. Now that, of course, is not all the solutions. So, for example, flat space is a solution if the cosmological constant is 0, and anti-de Sitter space is a solution if it's negative. But the first kind of solution that was looked at are linearized solutions. Let's take the cosmological constant to be 0. And if you look at the linearized theory, if you have the pure Einstein theory, there are no degrees of freedom whatsoever. But we've added a term. The Chern-Simon term has 3 derivatives in it. So we've added more derivatives to the action, which means that we need to pose more initial data, and the constraints in gauge freedom are no longer enough to eliminate all the degrees of freedom. And now if we look in flat space, in fact, we have a propagating degree of freedom, which is called a massive graviton. And this massive graviton has a positive mass mu. It's related, it's the inverse of that coupling that of the Chern-Simon term, but negative energy. So it's always a little confusing how something can have positive mass and negative energy, but in fact it's easy to think of examples. Suppose we just take a scalar field and we change the sign in front of the action. Now, if you change the sign in front of the action, you don't change the equation of motion. So the pole in the propagator is at the same place. You don't do anything to the mass, but you do change the energy. So if you have a wrong sign scalar field, that's a simple example of something with positive mass but negative energy. Now, Desser-Jakiv and Templeton proposed that what we do about this is to take Newton's constant to be negative. That seems to run into trouble. The black holes, for example, will have the same sign energy. And so they'll become negative energy if we flip the sign of Newton's constant. So I want to do something different. I want to study this theory in 3-dimensional anti-de Sitter space. So if the cosmological constant is negative, then 3-dimensional anti-de Sitter space will be a solution. Now, if the graviton mass is very large, this should be essentially like studying the theory in flat space. If the Compton wavelength is small compared to the ADS radius, there should still be these negative energy excitations. But something interesting can, and we will see does happen, when the Compton wavelength of the massive graviton becomes the same as the anti-de Sitter radius. So we take anti-de Sitter space, we expand about it. Anti-de Sitter space, of course, has 6 killing vectors, which form an SL2R generated a global SL2R cross SL2R symmetries. And if we want to study excitations about anti-de Sitter space, the best way to characterize them is by saying what their SL2R cross SL2R representations are. So I won't go through this. This is kind of a long calculation, but one that we're familiar with in many other. It becomes especially long for this massive graviton because the action is not the gauge invariant. The equations of motions are kind of complicated. But what you do is you look for eigenstates of L0 and L0 bar. So we're just trying to solve for the explicit wave functions here, which this is sort of energy plus angular momentum and energy minus angular momentum. And then we demand that they be highest weight states, in other words, annihilated by L1 and L bar 1. And after a lot of work, one finds that the equations of motion of TMG define 3 kinds of propagating degrees of freedom. The first 2 have weight 0, 2, and 2, 0. These ones not only solve the TMG equations, they also solve the Einstein equations. And these are the usual massless left and right moving boundary gravitons. And when we think of quantum gravity on ADS-3 as a conformal field theory, these are the objects that are the descendants, the L-2. The highest weight state is an L-2 descendant of the identity. Now, by the way, when I'm talking about highest weight here, I'm talking about highest weight SL2R cross SL2R, not highest weight Virasoro. We know that, in fact, in quantum gravity on ADS-3, this SL2R squared gets embedded in 2 copies of the conformal group. Now, in addition, we find a third representation, the massive graviton. And when mu L is very large, this representation looks a lot like a massive some kind of massive scalar, or I guess it would be massive spin 1. No, well, some kind of very massive representation. But notice that something very special happens when mu L goes to 1. Then this becomes 2, and this becomes 0. So the weight is degenerate with the left-moving massless graviton. And if you look at the equations in more detail, not only is the weight the same, but the actual form of the wave function for the massive graviton approaches that of the left boundary graviton as mu L goes to 1. And another interesting thing that you find is that if you compute the energy of these, now in Einstein gravity, these guys always have non-zero energy, but we've added another term to the action. When we add a term to the action, there's extra boundary terms in the expression for the energy, and it changes the expression for the energy. This was worked out a long time ago by Deser and Tikin and Krauss and Larson. And you find that the energy of these 2 things goes to 0. And in fact, that kind of had to happen because, remember, this one was positive energy, and I said these guys were negative energy. So if their wave functions agree at mu L equals 1, their energy better agree. And that seems to be a puzzle because one is positive and one is negative, but in fact, one of their energy goes from 0 to 0 from below, and the other goes to 0 from above. So it seems that something very interesting is going on at this point. And indeed, it is very interesting. And the way to understand it is to look at something called the asymptotic symmetry group. So the asymptotic symmetry group is as follows. Let's suppose that we're doing quantum gravity on some space, or of course this can also talk about the asymptotic symmetry group in gauge theories or anything else. And you have some set of boundary conditions which are part of the definition of the theory. Then there's a set of allowed diffeomorphisms which preserve the boundary condition. And then, given some dynamics, a subset of these are trivial. In other words, in the quantum language, must annihilate physical states. So in general relativity, if we take a diffeomorphism with compact support, that has to annihilate every physical state. But on the other hand, if we take a diffeomorphism which goes to a constant d by dt at infinity, that should not annihilate physical states. That gives the energy. So in four-dimensional general relativity, time translations are not trivial diffeomorphisms. So diffeomorphism is trivial if it vanishes, including the surface terms which have to be added, when the constraints are applied. So then we define the asymptotic symmetry group as the allowed diffeomorphisms modulo the trivial diffeomorphisms, and it's typically a finite dimensional group, though it becomes bigger in 3 dimensions. So physical states always have to be in a representation of the asymptotic symmetry group, and they always have to be annihilated by the trivial diffeomorphisms. Okay, so this story about the asymptotic symmetry group is pretty straightforward and simple in 4 dimensions, but it becomes extremely subtle in 3 dimensions, as was famously pointed out by Brown and Hainaut for the pure gravity case in asymptotically anti-de Sitter space. Now, the Brown-Hainaut story needs a little bit of modification when you add the Chern-Simon term. And that was worked out by Krauss and Larson a few years ago. And what you find is that the asymptotic symmetry group has is generated by 2 copies of the Virasoro algebra, a right Virasoro algebra with this, and they also, amazingly, were able to compute the central charge just from the surface terms. And you have a right Virasoro algebra with this central charge and a left Virasoro with this central charge. And you can write out the explicit generators. I'm taking the formula here. A number of people have worked this out using different formalisms. I'm taking a formula here from Krauss and Larson. And you can write out explicitly what the generators reduce to when you apply the constraints. They become surface terms. And the interesting thing here, so they become surface terms of components of the fluctuation of the metric folded in with the conformal transformation parameter. And here are the modifications that Krauss and Larson worked out, which also agree for the energy and so on with Deser and Tikin when you have this Chern-Simon term. And the interesting thing is that when mu L is equal to 1, epsilon minus, which parameterizes the left-moving conformal group, simply does not appear in the generator. So that means that left-moving conformal transformations at this critical point become trivial. And the asymptotic symmetry group collapses from the generators collapse from 2 copies of the Virasoro algebra to 1 copy of the Virasoro algebra. So that means that, these epsilon minus transformations are trivial. Physical states have to be annihilated by the left-moving conformal transformations, which now are pure gauge transformations. And therefore, we conclude that the theory has to be chiral. Now, I showed this, the argument I just gave is in a recent paper that I wrote, maybe a week and a half ago. And in an earlier paper with Wei Li and Wei Song, we noted the following thing, that the left-moving and the massive gravitons become null states. The BTZ black holes, if you look at their modified formula for the entropy, they all have E equals J, and everything we knew about was becoming chiral. And furthermore, the left-moving central charge goes to 0. And in this paper, we speculated, or we conjectured, that the asymptotic symmetry group should just be one copy of the Virasoro algebra, though for some reason the simple argument I just gave didn't occur to me till a little bit later. So therefore, this theory is mu L equals 1 theory, unlike other theories on ADS3, is a chiral CFT. Now, we've shown that it's chiral. What we haven't shown, and what I think is a difficult problem, as this kind of problem typically is in general relativity, that the energy is positive. Or in this case, there's only one energy, the right moving energy. The left moving energy vanishes by diffeomorphism invariance. So that motivates the conjecture that this should, hopefully this exists as a quantum theory, and since the states transform under one copy of the conformal group with this central charge, its dual CFT has to have C right equals 3L over G. Now, by the way, if the theory exists and is unitary, then we will automatically have an explanation of the entropy of the black holes in this theory, because we can, before even knowing what the theory is, we know the asymptotic growth of states, if it's unitary, from the central charge formula. Okay, now, there have been quite a number of purported counterexamples since we wrote our first paper, but before I proved that it was chiral, of modes that were supposedly not chiral. But, well, I don't want to go into all the details of how these counterexamples all fail, but none of the papers took into account the fact that the different left-moving states were actually gauge copies of one another. And there simply is no room in this theory to have any non-chiral modes, because there's no left-moving Virasoro algebra for anything to transform under. Now, this is a little bit of an aside, but I think it's an interesting one, and you'll see a little later in this talk. Oh, Jesus. Why these states are interesting. There are other ground states of, thank you. There are other ground states of these theories, so-called warped ADS3s. And there's a very interesting and involved story here, which is starting to unfold. Warped ADS3 is to ADS3 what the squashed 3 sphere is to S3. And it's possible, even though all these theories away from the chiral point are unstable on ADS3, it could be that warped ADS3s are stable ground states. And the warped ADS3s have a lot of structure like the regular ADS3. Again, I'm going to have to go through this quickly, but I want to say the relationship of this to Wittens' paper, 3D Gravity Reconsidered, that he talked about at Strings last year. So Witten proposed, having sort of given up on the Chern-Simon gauge theory approach, he proposed an end run around the problem, which was, let's just write down the answer. What could the answer be? And he said, well, here are the consistency requirements. It has to be modular invariant. There can't be any primaries below the black hole mass, because then we wouldn't be calling it pure gravity. And then he made an assumption, which he emphasized was not very well motivated, that the partition function holomorphically factorizes. Now, in chiral gravity, these consistency requirements remain true, but this is Witten's assumption moves into the consistency requirement column. Because chiral gravity, it can only depend on, it's chiral, so there is no left-moving partition function. And so if chiral gravity exists, we already know its partition function. Well, I suppose we don't quite know that this assumption will hold, but I think it should. And it's probably, the partition function is that formula that Wittens wrote down in terms of Hecke transformations of J functions. Indeed, there were several tour de force papers on doing the sum over Euclidean geometries, and for pure gravity, you could interpret these papers as showing that the assumption of holomorphic factorization was wrong. However, if you redo this discussion for chiral gravity, the action of chiral gravity is complex in Euclidean space, so you get a complex partition function. Also, all the saddle points of chiral gravity are Einstein metrics, and all the real saddle points are Einstein metrics. And so basically, you just get to copy that whole calculation. And when you do that, you get these, copy the calculation, you get this formula for the J function, and the coefficients in the Q expansion of this J function are integers. And so the fact that if you do the Euclidean path integral for chiral gravity, you get a partition function with integer coefficients. It has to be integer because it counts some number of states. That's some evidence that this quantum theory actually exists. Okay, now I'm going to, the last 5 minutes, I'm going to move on to a new topic. What does this have to do with the real world? Well, surprisingly, it does. And now I'm going to talk about some very recent work, which maybe I shouldn't be talking about because it's not completely finished, and maybe it could still collapse, but that chances look small enough that I'm willing to stick my neck out now. Okay. So this whole subject that I've been discussing is very closely related to the study of Kerr black holes. So an extreme Kerr black hole has angular momentum saturating the cosmic censorship bound. It has zero Hawking temperature, but even though the temperature is zero, the horizon has non-zero area and it has an entropy. Now, in fact, there's a tendency for black holes to gather more and more angular momentum as they're fed from their accretion disks. And many black holes are very nearly extreme. For example, this one by McClintock et al., which has 14 solar masses, is within 2% of extremality. So extreme Kerr black holes are things that we see in the sky. Now, one of the properties of a Kerr black hole is that as you approach the near horizon region, you have to rotate around with the black hole. And for an extreme Kerr black hole, you have to rotate around at the speed of light. So this is very much like chiral gravity. It's sort of a physical picture of what chiral gravity is. Everything is forced near the horizon of black hole, extreme black hole. Everything is forced to move counterclockwise around the black hole. Now, this analogy can be made much more precise. Almost 10 years ago, Bardeen and Horowitz looked at the near horizon extreme Kerr, which we call the neck geometry, and found that there's an enhanced SL2R cross U1 isometry. Furthermore, as was noticed by some other people later, if you fix theta and look at a cross-section of Kerr at fixed polar angle, you get it's precisely a quotient of one of these warped ADS3s that I was talking about before. And in fact, at a very special value of the angle, it's a quotient of ordinary ADS3, which means if we ignore the theta direction, we have one of these warped ADS3 or ADS3 black holes. So, well, when you see ADS3, bells should start ringing and we should start thinking conformal field theory. And indeed, there's no reason that the same kind of, so now we use the same logic and we compute the asymptotic symmetry group for this neck geometry. And indeed we find that the asymptotic symmetry group contains a Virasoro algebra. And just like Brown and Hanot, we don't need to know the microscopic theory to compute the central charge of that Virasoro algebra. We find that it's 12 times the angular momentum of the black hole, of course, divided by h bar. Now, that's not the end of the story. There's the famous, everybody knows that for Hartle-Hawking, that there's a natural ground state. For Schwarzschild, there's a natural ground state, which is the Hartle-Hawking state. And this has been generalized by Frolov and Thorne some years ago to a state for Kerr. And when you get to the extreme limit, you might think that it becomes a pure state. So if you take the Hartle-Hawking state for a charged black hole, when you get to an extreme charged, the extreme Riesner-Nordstrom, the Hartle-Hawking state becomes a pure state outside the horizon. But that's not the case for extreme Kerr. In a sense, what's happening is that the left movers that I was talking about, the guys spinning clockwise around the black hole, are thermally excited at a dimensionless temperature in the units of the radius of the black hole, 1/2 pi. So now we've shown that quantum gravity on the neck geometry is a conformal field theory with one copy of a chiral conformal field theory. Here's its temperature. Now we use the Carty formula. In bingo, we get the number of microstates of that CFT is 2 pi j over h bar, which is exactly the Bekenstein-Hawking entropy. So I think this is one of the first times that this kind of logic has been used. We've been frustrated in our attempts to understand black hole entropy, but here at least we're starting to get at the entropy of some really microstates, learn something about microstates of something observed in the sky. So the conjecture that I'd like to end with is that the black hole GRS 1915 is dual to a C-left conformal field theory, which this value of the central charge, which is it's the number of units of number of integers of angular momentum it has times 2 pi, and that's the end of my talk. Thank you.
We have time for a few questions.
Jeff is waving his hand.
Jeff, yeah, push the button in front of you.
Like that?
Yeah, then you need it.
I was wondering whether, I was jokingly going to ask how that compared to the number of elements in the monster, but seriously, is there any connection? I mean, Wittens was, in his paper, was suggesting some connection between pure 3D gravity and the monster because of the fact that the J function, once you take away the constant term, is the partition, has a is a partition function for a conformal field theory which has monster symmetry. And I was just wondering, since you have this purely chiral theory, whether you see any connection to some possibility that there might be monster symmetry acting on the space of...
Well, my understanding is that people could take this question. Maybe I should throw this question to Davide, but my understanding was that these you couldn't have a representation of the monster symmetry in these 3D partition functions beyond k equals 1. These extreme old CFTs couldn't. They might exist, but they couldn't fall in representations of the monster symmetry. On the other hand, the partition function for Kerr could easily be some kind of symmetric it also has to have a chiral partition function. And notice that the central charge was 12 times the angular momentum, which is half integer. So So the same kind of logic will come in there, except we don't have this business of the gap. So it's natural to expect that the partition function might involve these symmetric product spaces of these orbifolds of the Leech lattice that represent the monster group.
Nikita?
So maybe not in 3D, but maybe in 4D.
So typically when you have a limit of conformal field theory with central charge going to 0, some states becoming degenerate, you get logarithmic CFT. So this argument that you have a coefficient in front of a transformation which goes to 0 is usually too naive. Are you certain it's not the case in your story?
Sorry, what? No, it's not too naive. It's true. The asymptotic symmetry generator is just 0.
There are many examples where it's not so, but I don't know about your story, so I'm just asking.
Did you see any other raised hand? Well, if there are no more questions, let's thank our speaker again.